So we're now nearly at the end of our coverage of key operators in Project Reactor, both in fluxes and monos. And so what we're going to do here is take a look at yet one more case study. And this will give us a chance to talk about some other really interesting things that we have only touched upon briefly here, including our own custom subscribers, which we'll talk about here. And we'll do this in order to, as usual, create, multiply, and display big fraction objects asynchronously and concurrently. It'll also show some other mono operators, including an interesting one called flat map many, and you'll need to understand flat map many in order to be able to properly do assignment 4B. So we're also going to talk about this interesting implementation of subscriber called blocking subscriber, and that will be a useful class that you could use for other examples, other applications. And it also can be used to work around the lack of a blocking subscribe operator. For some reason, the Project Reactor framework does not have a blocking subscribe operator, whereas the RX Java one does. So this is kind of a way to work around that particular limitation. So as usual, you can find all the code here in my GitHub repository in this folder. So we're now in my IntelliJ project for case study ex4. Let's click on the ex4 file. As always, this is the main entry point into the test program. As you're going to see here, we register a couple of test methods, one of which has got a ridiculously long name called test fraction multiplications blocking subscriber, and that's what we're going to take a look at first. And then we're also, in the next part of the video, going to talk about test fraction multiplications streams. And as usual, after we register both of those things, we run the async task barrier run task method, which lets them run in the background, and then we block the calling thread waiting for the results to finish. So let's go ahead and take a look here at FluxEx, which is all where the fun stuff takes place. And we're going to start by taking a look at test fraction multiplications blocking subscriber, which again is a bit of a mouthful, but it does some really cool stuff, and it'll give us a chance to talk about a helper class called blocking subscriber that we'll get to here in a second as well. So as usual, we're going to start out the walkthrough here by creating a string buffer, which needs to be a string buffer because the things are going to be done in the background. We then go ahead and indicate that we're going to start the asynchronous processing. We create ourselves an array of big fractions. Not really interesting what they do, but that's what they do. They have numerators of 100 and various denominators, none of which are 0, so we shouldn't get exceptions. And then down here, we're going to create ourselves an instance of a helper class called blocking subscriber. We're going to look at blocking subscriber here in just a second, but it's really cool. And what we do when we create a blocking subscriber is we pass to it 4 parameters. The first one is essentially a consumer that's going to be used every time we get a next item that's emitted as part of the processing that runs when subscribe is called. And this is just going to add each fraction that comes through this thing to a string buffer, and when we're to the string buffer. And then when we're all done, if everything goes well, this runnable here will display the results. If something goes wrong, a throwable will occur, and we're going to append the error message and display the results. That doesn't really happen here, but we need to be prepared for it. And then we also provide what is essentially the back pressure value, which in this case is the non-back pressure value, which is max value. So that just says, blast the stuff through as quickly as you can. Don't worry about trying to apply back pressure. So that's what we create for blocking subscriber. I will show you blocking subscriber in just a second. Once we have our blocking subscriber created, we then go ahead and will create a random large big fraction. So we make a large big fraction. You've seen this method a gazillion times now. It basically makes a very large numerator and a much smaller denominator, and it combines them together to make a big fraction. And it's reduced. And then we go ahead and transform the item emitted by this mono. So we take the random big fraction that was created, and then we forward it to the returned flux. And so what we're basically doing here is we're taking that stream of big fractions. Remember, we had this big fraction array up here. And what we're basically doing here, the way to read this is sort of, it's kind of like a parallel for loop, if you will. We're saying, for each big fraction in this array of big fractions, multiply each of those big fractions in the array by the random big fraction we created here. So it's kind of like, say, make a big fraction, and then for each fraction in the array, multiply that one random big fraction by each of the elements in the array. So it's just sort of like a for loop, if you will. Except here, of course, we're using the flat map concurrency idiom to do the whole thing concurrently. And you'll see how this works. So we take each big fraction and we go ahead and multiply that big fraction. So for each of these things, we're going to multiply it. And here is what multiply fraction does. It goes ahead and will multiply the big fractions by a constant. And that also runs in the background in a thread pool. And so basically everything gets processed here. The last thing we do, because of course this is going to be a flux stream, is we go ahead and we pass blocking subscriber, which is this subscriber we created up above. Go take a look. Blocking subscriber is this thing we made up here. And we pass that to the subscribe operator. And the subscribe operator then is going to use this custom subscriber to do all the things that are required for subscribing. So it's kind of delegating to the blocking subscriber. That's the way to look at it. So let's go ahead and take a look at what blocking subscriber does. Now, one more thing, sorry. So remember, subscribe doesn't block. Subscribe is going to return right away. That's the whole point. It's asynchronous. So we want all this processing to take place in the background. So what we're going to do here is we're going to say, hey, blocking subscriber, please wait until all the asynchronous computations are done. So this await method here is essentially a barrier synchronizer that doesn't allow the calling thread, in this case it's the thread that's going to be the thread that's calling test fraction multiplications blocking subscriber, that thread is going to block until all the computations are finished. And we do that so that we don't fall off the end until we're done. So, of course, because of the fact that under the hood we're using the async task barrier, we don't actually have to do it this way, but I'm just doing it this way because I want to show you the concept of blocking subscribers. So let's go ahead and take a look at blocking subscriber and see what it's doing, how it works. So we go to blocking subscriber, and you can see that blocking subscriber is just a class we wrote that implements the pre-existing subscriber. And it's going to do a couple of really cool things. First, it's going to create a field called countdown latch. And countdown latch is going to be used as a barrier synchronizer to make sure that the await call doesn't return until all the asynchronous computations are finished. So that's how that gets used. For those of you who will be taking my course in the spring, we'll be talking about countdown latch there as part of our coverage of barrier synchronizers. So you get a chance to learn about synchronization. You've probably noticed that we've talked almost nothing in this class about synchronization. We've talked almost entirely about parallel computations or asynchronous computations. And the reason we didn't have to talk about synchronization was all the mechanisms we looked at, streams, parallel streams, completable futures, Project Reactor, often eliminate the need for synchronizing things because you're not sharing anything. But when we talk next semester, we're going to talk about concurrent programming as opposed to parallel programming. And in that context, synchronization turns out to be very important. So we'll talk about a whole boatload of synchronizers. So there'll really be absolutely no overlap whatsoever between the topics we've covered in this semester in parallel functional programming and the topics we're going to cover next semester on concurrent object-oriented programming. Never the twain shall meet, even though they're all part of Java, which is interesting. Then we also have a bunch of fields that keep track of the various parameters that subscribe needs. So a consumer, an error consumer, and a complete consumer, which probably actually should be called complete runnable. Let's see if we can refactor that, because that's kind of a dumb name. It's not really a consumer, it's really a runnable. And then the last thing we have is this value, which is going to indicate the number of requests that we want to make to the upstream publisher, which in this case is going to be max, the max value for, I think it's long, but in other cases could be other values. Let's just go back to double check what it is. It's, long max value. Okay, so here is the constructor for blocking subscriber. You can see what it does is it makes a new countdown latch with a value of 1. Without getting too far ahead of ourselves, we'll cover this next semester. A countdown latch is a very simple barrier synchronizer that has a count. And as long as the count is greater than 0, anybody who's awaiting will block. Once the count drops to 0, anybody who's awaiting will get a chance to go. You can kind of think of it like a stoplight, right? It's either red or green. And so in this particular case, we give it a countdown latch initial value of 1, which says wait until someone decrements the count, and then anybody who's waiting can go ahead. You could make it n if you wanted to have multiple threads await and go, but in this case, we just have 1. So we create a countdown latch, and then we make consumer, error consumer, and complete consumer, which I should, again, change this to complete runnable. And let's make this be runnable as well, because it really is a runnable, not a consumer. Okay, so that just stashes those fields away. Here's what await does. As you can see, what await does is it just calls the await method on the countdown latch, which will block the caller until that count drops to 0 atomically. And here's onSubscribe. OnSubscribe is the hook method that's called back automatically by the Reactive Streams Framework Project Reactor implementation to say how many events do you want before you wait for the next chunk of events. And we just say, in this case, I want all the events, throw them at me as fast as we can, because we give long max value. Then let's take a look at the various other methods. These are all methods that are overridden because we are implementing the subscriber interface. So on next, and you can see all it does is it just accepts the element t into the consumer, which we stashed away in the constructor. That's what we did up here. You can see that on error accepts the throwable into the error consumer and releases the latch because an error has occurred, so we don't want to block anymore. And then the more common case, which is what happens when things complete normally, when onComplete is called, then we forward that to mComplete runnable run, which will go ahead and do whatever the shutdown hook is. And then we release the latch. So that will decrement the count by 1, which means that anybody who's over here, blocked, waiting, will be able to continue on their merry way. One other thing I want to draw your attention to here real quick is the use of flat map many. So what flat map many does is it takes an item that's emitted by a mono, and then it assumes that the item that's emitted is a flux, and it returns the flux. So it's basically a way of going from a mono to a flux. So whenever you need to convert from a mono to a flux, flat map many is a good thing to look at. And when you look at the assignment 4B server side, which is part 1, and that's the video that's called part 1, you'll see that there's a case where you need to use flat map many in order to make that work. You're converting a mono to something to a flux of something. Okay, so that is basically an overview of the first part of the case study ex4 example.